Okay, so we'll continue. Okay, so this was actually so far the easy part of today's lecture. We'll now get to the more complicated part. But first, we'll retake the issue of dephasing, rephasing, or echo formation. And this is a classical example, and this is we're going to look at vector tips of two vectors representing two magnetizations, one that precesses fast in one direction, the other one precesses slow in the other direction, and the vector tips are represented by the hare and the tortoise running on a circle. So here they are, here's the hare and the tortoise. This is a circle with radius r. We have a velocity that's given by the angular velocity times the radius. So we'll start out at time 0, they're in phase. Here's the fast magnetization, that's the hare, and the tortoise is the slow magnetization, and they just represent the tip of the magnetization running on this circle. So at time 0, they're both at the same position. Then they, in a certain amount of time, they will have run, we'll call this time TE over half. Since the hare is running fast, he'll have run a longer distance compared to the tortoise, which has run a shorter distance. So here they go, they run, the tortoise in clockwise fashion, the hare in counterclockwise fashion, and the hare has gone from here to here, the tortoise from here to here. That's a different distance corresponding to their slower speed. Now at time t half, a guy tells them, you're running on a circle, now you run in the opposite direction. You stop, turn around, and run in the opposite direction. So it's a 180-degree turn at this time, and now they're here, and now they're running back for again the same time, and since this distance has to be equal to that distance, and this distance has to be equal at that distance, they have to arrive at the same time, and this is exemplified here as they are going back, and after the same time they are running, coming back at the same position and finding each other at the point of start. Okay, so that's now a hare and a tortoise. Now you can imagine a whole family of tortoises and hares doing this, all running at different speeds, because I haven't told you what their speed is. It's independent of their speed. It could have been any speed that they had. So you can imagine thousands of hares and tortoises running around. They will all end up somewhere on the circle at different points on the entire circle. They will all flip their direction at the same time, and they'll run back at the same speed, and they'll all end up again at the same point where they started at the beginning. And since I now represent the vector tips, that's the orientation of the vectors, they'll all be distributed at TE equals half. They'll distribute it on the circle, but at 2 times TE half, that is at TE, they'll all be back to the origin and at the same point, and that's where we have the echo formation. And so TE is called the echo time for that. Okay, so now to understand what follows, we'll have to do a little interlude and ask ourselves the question, what is the effect of when one applies a gradient? So when one switches on the current in the gradient coil. So we'll start out with this experiment here. This is a gradient along X. We have here the condition that these two areas are in magnitude the same and one is negative. This will give us echo formation. We have seen that before the break. And this is what we call TE. We'll call this time tau here. This is 2 tau. And now we'll apply a current in a different coil, so we'll produce a gradient along Z, which has this temporal function. So it's just 0, and at some point we turn it to a negative value, and at time tau we'll turn it back off. That's the gradient along Z. We're interested in this area, of course. So this is what we'll call the sequential application of the gradient along Z with respect to the gradient along X. And now this is the second scheme. We'll draw again the gradient along X. That's actually the same thing as on the left, so I'll go a bit quicker. And now we'll apply the gradient along Z, not before one starts to switch to gradient along X, but simultaneously. So the gradient along z will be applied at the same time as the gradient along x is turned on negatively. We'll have again the same time points, and we'll define again this time here as the echo time TE. That's what we call the gradient applied simultaneously. So now the question is there a difference on the echo? Is there a difference on the signal between these two schemes? So let's look at this. The magnetization here on the left at time tau is given at the magnetization at time 0. We'll assume there everything is in phase, times the effect of dephasing from this gradient. So that's I gamma gz times z times tau. That's this area here. And on the right, we have the magnetization at time tau is given by, we'll assume the magnetization is all in phase, is M0. So it's this term. So clearly at that time, the magnetizations are different. At times 2 tau, we have the magnetizations at time tau times the term from the x gradient. So it's e to the minus gamma, etc. We can write this by substituting the magnetization of tau in here. We'll have this expression here. What's the magnetization at times 2 tau here? So the magnetization at times 2 tau is equal to the magnetization of tau times the effect of the gradient. And remember, the phase of the gradient is given by the scalar product of the gradient times position. And now in this time, we no longer have a single gradient in one direction, but we have the gradient vector. So this is equals to the scalar product of the gradient vector times the position at this point, times tau, because the duration here is tau. Okay, this is where this comes from. And so we rewrite this, we divide this out, rewrite it slightly differently in an equivalent fashion, and what we observe is that these two expressions are mathematically identical. If you look at this, these two phase terms are identical, m of 0 is the same thing. So in conclusion, the application of two orthogonal gradients simultaneously or sequentially has the same effect on the magnetization phase. That is how the magnetization vectors spread out in the transverse plane. The reason I'm introducing this to you is I could try to do the course from now on with the scheme on the left on the gradient applied sequentially, but the slide will be even more difficult to read because we have to use a lot of space for it, and that's why I just want to introduce that this and this is the same thing. This is conceptually easier to understand than what's going on here. When you can just, in what follows, say, okay, I know that this equals to this, and this may help in understanding what's coming after this. Okay, so then we have the magnetization at TE is equal to the magnetization 2 tau, and then we have times the effect here of the gradient after this time point. Or if we include all the terms, then we start out with the influence of these two gradients plus the evolution after here. And actually, you can see now at TE, with the condition of tau equals TE half, we find that actually the magnetization at times TE, that is at this point here, is given a magnetization at the beginning. This one, if we're looking at the magnetization either at this point or at this point, it's equal to that magnetization at the beginning, or that one, times the effect of the z gradient only. As we had seen before, a gradient switch negative and positive will have no effect on the magnetization phase, and therefore the gradient along x has no effect at that point. It's only the gradient along z that has an influence on the phase of the magnetization. Okay, and so now I want to introduce a basic imaging sequence, MR imaging sequence, so-called gradient echo sequence. We'll start to put in all the elements, almost all the elements that we need, but just first the introduction of the gradient echo sequence. So what we need at the beginning is an RF pulse. That flips the magnetization by alpha degrees. We'll start out with Z magnetization before the pulse. This will be one time point to consider. And now we'll employ a gradient, say, along x. It doesn't really matter what it is. But what matters here is that we actually call this gradient is actually called frequency encode gradient. Along x, it'll be first switch negative, switch positive. So that we are familiar with. this area plus this area together has to give 0. This will define the echo time, the echo formation, and this will define the echo time of this sequence of the signal, and this is where one has the maximum signal occurring after this gradient switching. Then we do slice selection. So we've seen earlier before the break, we've seen an RF pulse applied on resonance only tilts the magnetization that corresponds to the resonance condition. So if one applies a gradient together with the RF pulse, only the magnetization in a given slice is being tilted by alpha degrees. So that's the slice select gradient here. One has to pay attention to this area being equal to this area. One wants to mitigate these effects. And there is an issue here. Why does one have to do this? And the issue here is it's another way of echo formation along the slice select direction. Why does one do that? The reason is one cannot switch the gradients infinitely fast. And that's why if you see now here in this drawing, it's no longer going from positive to negative vertically with a slope of infinity or minus infinity. We have a finite slope here. It's just reflecting the fact that the amplifier that has to drive the current into the gradient coils can produce a certain voltage rail. It's typically something like 400 volts or so, but it has to overcome the inductivity of the coil, and this gives a finite response time of the system. So this takes some time for the gradient current to build up, and this is why this slope here is not infinite, but it is a finite slope here. So finite rise time is the issue here. So we'll have dephasing of magnetization during the application of the RF pulse, and then one produces rephasing here. If one were not to apply this negative gradient, then this would create dephasing of magnetization, and ultimately, with time, this will go to 0, just like an FID in the presence of a gradient. So the dephase faster the magnetization, and if one weren't to do that, one would have no signal, and it would be a quite pointless experiment. So in principle, if you just look at this effect here, you will have at that point echo formation if you just had this gradient and this RF pulse. So to put it in more general terms, the signal is proportional to the integral over the slice of the magnetization times this complex factor here, which is the integral of the gradient with time. This has to be maximal, and this condition of this to be maximal requires, in generality, that this integral is 0. Okay, that's the mathematical rehash of saying that this area, which is positive, has to be equal to this area, negative. Then you just integrate over time, so the integral from here to here has to be 0. What's behind it in all generality is this integral condition. Then the phase term here will become 0, so we have a spatially independent phase of the signal. Typically, the slice gradient and the frequency encode or read gradient are orthogonal. So one's along x, one's along z, or vice versa, or y, whichever. Then the signal is acquired here. Here's the echo. Here's again the rise time here. You see that the rise time is finite. So one needs this time here. One does the data sampling of the signal here. And that's actually what the computer sees. The computer sees, after it's gone through the analog digital converter, the computer just sees a bunch of numbers that are stored in memory sequentially in an array. The first half of the echo is also measured. That's a reason because it produces more signal. There's additional data points that can be measured. Okay, so that's, in summary, the entire so-called gradient echo sequence. It's the basic building block of an MR imaging experiment to produce an MR image. We have in this frequency encode, slice selection as an element, but we have one objection here. Does this produce an image? two-dimensional image. Okay, Z is selecting the slice. X in here is encoding with Fourier transformation at dimension X. We're missing the third dimension, that's Y. Okay, so now we'll come to the hard part of today's course. And that's how is the information encoded to produce a two-dimensional image. So we'll start out again with the gradient echo sequence. Here's the alpha degree pulse, the slice select gradient, frequency encode gradient. At this point we have echo formation. This is where the rephasing occurs. These two areas are the same. This is what an echo looks like at this time TE, the data sampling, and that's where we have the signal. And now comes the third gradient, and that's the phase encode gradient. That's going to encode the third dimension. And this is the hard part. So we're going to try to rehash it in several ways. I'll we'll review this topic for a few minutes in next week's course. So we'll have the phase encode gradient, and that one is now just turned on for a short period of time here in red. And that's the now complete sequence, except this experiment is now repeated every TR seconds by changing the amplitude of the phase encode gradient by delta GY. Okay, so you have here a certain amplitude of the phase encode gradient. This gives you a certain area. You do that once, you wait TR seconds, then you do it again, but now the phase encode gradient, the amplitude has changed by delta GY. This is the decrement in this case, or increment. Decrement, increment, just same thing with a different sign. Do it again. I'll decrement now again by delta GY, and so on. I'll do it again. I'll do it again. I'll do it again, etc., 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 etc. And every TR seconds, the same thing is repeated. An alpha degree pulse, slice select gradient, readout gradient, and in there is the phase encode gradient that is changed linearly with time. That's the experiment that's being done. As a reminder, slice select gradient is perpendicular to the frequency encode or readout gradient, which is perpendicular to the phase encode gradient. We'll keep it that way. It can be more complicated in reality, but this is complicated enough. So that's the essential imaging experiment. Now we'll have to understand how this creates a two-dimensional image. We can typically separate an MR image sequence into three phases. One is excitation, typically associated with slice selection. Then there's the phase encoding time period, where the second dimension is encoded, and here's the frequency encoding and echo formation, the third time period in the experiment. Time frame for this is typically on the order of tens of milliseconds. It can also be a few milliseconds, but to give you an idea what we're talking here. Okay, so let's try to understand how this phase encode direction gradient encodes the second dimension. We'll consider a two-dimensional object in X and Y, and we'll look at a given voxel in this object at the transverse magnetization here, the vector depicted in each of these circles. We'll look now at the phase encode step 1. So we'll apply a gradient GY of time, and this is Y dimension. Now you can see for this position here, they've all turned to the same phase. The phase is a little bit different, phase is a little bit different, etc., etc. And then here it's the same thing, but now going in the opposite direction relative to this guy. So that's the effect of turning on a gradient for a few milliseconds here on the magnetization in our object here. That's a two-dimensional object with 7 by 7 voxels. Now we'll do step 2. We'll repeat the experiment, but now the gradient strength is twice as strong. And what will happen is, after having applied the gradients twice as strong, the phase is now twice as big for a given position in Y. So this phase with the orange gradient, twice as strong gradient, this phase is twice as big as the phase was with the first step, applying the first step. Same here, same here. Here it's always the same because there's no effect. So that's a gradient along y applied for tau milliseconds. We can also express this in complex plane. So we'll take the y direction as imaginary, the x direction as real. So the phase of the voxel magnetization is then simply given by this expression here. So after applying the phase and cogradient along y for tau milliseconds, then we have the situation here. So this is now the same as here. This won't reproduce well on PDFs, but with the animation this should work. So now we have, after phase and cogradient, we have this distribution of magnetization. You can see no spatial dependence along x, because we have only applied a gradient along y, so everything for a given position y has the same effect independent of x. It's only along y that there's an effect on the magnetization. And now, at this time point, we'll apply a gradient along x, the frequency encode, and what you will see now is that the magnetization in these voxels now precesses faster for those that are further away. So that's these guys here, or these guys. They just go in opposite direction. The ones that are on resonance don't move. So that's our on resonance or our rotating reference frame. And here the frequency of precession increases linearly clockwise, and here it increases linearly counterclockwise. The difference in y is they have all, along y, different starting phases. Because we had applied this gradient here, we've given them different starting phases. Even though they precess now with the same frequency, which allows us to encode the position, they have different starting phases. But essentially what I'm showing you here graphically is what's happening mathematically with this term. Okay, so these are the two terms that describe the behavior of the signal during this x gradient here that's turned on. And I'll just rewrite it and express it now with the reciprocal space or Fourier space variable kx and ky. We can do that. This is just a mathematical transformation, and in math everything is possible. I'll give you some idea what we're talking about here. So that's the encoding, and essentially we have now two-dimensional information in here. The difficulty is how to understand that every TR seconds one increases the amplitude of one gradient, the phase and cogradient along y. How does this produce an image or information that allows us to produce a two-dimensional image? So what I'd like to make the point here is that this is actually equivalent to frequency encoding. We're talking about spatial gradient changing the phase, but it's the same thing as if you were to frequency encode. So we have frequency encoding, we turn on a gradient, we look at the signal, we Fourier transform, we get a projection. Now what I want to show you is to increment the gradient every TR seconds along y. The effect is the same as if you had turned on a gradient along y, at least seen from the computer. So we'll start out with the magnetization along the readout. This is here. When the gradient is turned on, it will dephase. So we have this position. In step one, we'll apply a gradient along y. So the phase is now shifted along according to the position in y and tilted by the readout. What we're now looking at here is not an object. We're looking at a single pixel in space. Okay, we're looking at just what's happening in time. This axis is the readout time, and now one repeats the experiment by turning on the gradient and fills that into the computer. So what we're looking at is the elements of the matrix that are being filled. But instead of talking about numbers in a matrix, we're looking at the magnetization vectors that are being measured. Okay? Somewhat. Okay. Well, step two, we'll have a stronger phase twist because the gradient is twice as strong, so that's the starting phase. We'll turn on the x gradient over time. This is what the computer will record through the digitization. We'll do a step three here. The phase, you can see the phase is now twisted even more according to the application of the gradient along y. Here, 3 times as much, and then by the application of the readout gradient, it is, after a certain time, it's twisted. For all of them the same way, but they have different starting phases. And we'll do the opposite now with a negative gradient. So we'll start out after gy, the phase is twisted in the opposite direction. Here was twisted upwards, here's twisted down or rotated. This is the application of the x gradient, etc. and so on. So these are, we have one more here, we'll do that again. So what we're looking at on the horizontal axis is the position, the phase of the magnetization vector with time during which one records the signal. On the vertical axis is what we have filled into the matrix in the computer after digitization, each time after the y gradient has been incremented or decremented from this value to this value. That's going from here to here. And here the phase represents the phase change at the position x equals 0. So nothing has happened but during the readout, it hasn't changed. And this is the position of, this is the phase in readout time for the position y equals 0. So the application of the gradient along y has no effect. No, I'm sorry. This is not position. This is where the gradient y was 0, and this is the point, the time point where the phase evolution along is the same. Okay, so along x, there's always the same rotation induced. Along y, there is a similar rotation induced. And now what I want to focus you on is the computer in the end records this data. It doesn't know which axis was the frequency encode and which axis was the phase encode. It just has a 7x7 matrix here. In each element of the matrix is a complex number. There's a phase associated with it, and you can just transpose it, and you still get the same matrix for this pixel. So in other words, applying the phase encode gradient, incrementing it, produces a change of phase that changes through here in the same way as it has changed through here. Now, if you have a phase that changes linearly with time, here, we know we have a phase that changes linearly with time, so there's a frequency associated with it. Now, the computer doesn't know that there's time here for this. For the computer, that's just a two-dimensional matrix, but this could also be just simply associated with the time. There's a phase that increments with the second dimension of this matrix, so there's a frequency associated with it. And in effect, you can take the data recorded like this, transpose it, and you can still produce an image. It has the same effect. Okay. Like I said, this is difficult. There's a different view. We'll try to rehash it next week. So we have the phase. The frequency is given by the change in phase. By doing these steps here, we induce a change in phase. We have to just associate to these different steps a time variable, a second time dimension, and then we have a two-dimensional data set. We Fourier transform it, this two-dimensional, we get a two-dimensional frequency set. So if we look now, here is a delta time. We can associate these differences with a delta time. That's like the dwell time of the analog digital converter. So our signal as for the nth step, for a given increment of delta gy, is given by the magnetization at our voxel times the effect of the phase encode gradient, n times delta gy, and this is the effect of the readout gradient. Okay, so we have, that is essentially the same thing, now just replacing the same thing as we've seen with applying a gradient before the x gradient, just do the gradient sequentially. But now we'll just do a variable transposition. We'll just replace these terms with different variables. We'll call the phase encode gradient gamma gy times tau, we'll call that ky, and gamma gx times t, the time during which we record, we call that kx. So that's a variable substitution. And now we get a signal as a function of kx and ky, which is given by the transverse magnetization in our pixel times e to the I chi x, x plus I chi y, ky, y. And this now was for one pixel. To get the entire object, one just simply integrates over the entire slice. So it's a two-dimensional integral of mx, of the transverse magnetization xy times this term. This was all for one pixel. Now we'll do it for the entire slice. So we have to integrate in x and y, two-dimensional integral. That's the expression what one gets. That's the signal that's being detected. And question, what does this resemble? Okay. We had before something with mx times e I kx times x, kx. Now we have two integrals. We have in two different directions I kx times x plus I ky times y. So what do we have now? We integrate instead of along x, we integrate along dx and dy. We go from one-dimensional integral to two-dimensional integral. We go from one-dimensional Fourier transform to two-dimensional Fourier transform. Okay, so that's what it is. We just do it's actually the inverse Fourier transform. So actually the magnetization measured in space is given by the inverse Fourier transform of this signal that we've measured as a function of kx and ky, which is Fourier space or reciprocal space, or as it is called in MRI, k-space. So the MR image generation is done. The data that's recorded in the computer from the experiment is two-dimensionally Fourier transformed, and that gives you the image of the object. And this is where MRI is fundamentally different from the X-ray based techniques. Okay. If this is difficult to follow, this is normal. It's not the easiest topic. There is on Moodle, there is a simpler description. I'll try to rehash it and give a different view on this encoding. Okay, the classical experiment, actually two-dimensional encoding was first introduced with spectroscopy, and there was a two-dimensional time encoding. So there's another way of looking at it, that you introduce a second time variable. That may help in the description, but we'll stick with the k-space, with this k-space formalism for MRI, because that's what all the literature is about and how this is done. So how is this information now encoded in MRI? We're looking here at the Fourier or reciprocal space represented by the variables kx, ky. That's the frequency direction or readout direction, the phase direction. This is along x, the gradient. That's the sampled signal. This is the phase encode. I'll forget now here about the RF pulse and the dephasing and rephasing that's needed to be done. We'll just keep it to the simplest point here. To just look at what's happening during the data acquisition. So we're going to look at these points here, measured by the ADC. They're filled in. Here's the phase encode gradient, turned on for a short time, and this is the readout gradient. And this is what the ADC acquires. That's what we get here. Okay. Now I'll do the next experiment after TR seconds. I'll turn on this phase encode gradient. The frequency gradient is the same. This will now fill in this line of data points in the matrix, in the computer, or in k-space. Remember, there's always a computer behind it, an analog digital converter. The data is digitized, and row by row is now the data filled into this two-dimensional matrix. Third one goes here. We'll do it again. And every time, the experiment, the sequence is repeated, but with a different phase encode gradient. And the different phase encode gradient means ky is different, because ky is given by gamma gy times y. Gamma gy times the duration of the gradient, or basically the area of the gradient times gamma. And again, and we'll do it again, and we'll do it again, and again, and again, again. Okay, that's when you hear the MRI, it goes bzz, 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 bzz. That's exactly what you hear. So you actually hear the filling of the two-dimensional matrix. You just hear the different phase encode steps in the experiment, and then we're done. We've got the data in there, and we can Fourier transform. So basically what this means is there's one line of K-space acquired per TR seconds for each excitation. We need, for an n by n matrix, we need n lines in the phase encode direction. Just for an indication, this time here is typically milliseconds. The TR is typically on the order of seconds, typically on the order of T1, can also be faster. So if one wants to measure a 256 square matrix, this time here is milliseconds, that doesn't really concern us. But if one has to repeat this measurement 256 times, then this means with a TR of 1 second, this basically means the measurement time is 4 minutes. So that's why when you go into any MRI and it goes bzz, 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 bzz for 4 minutes, that's essentially the filling of the K-space matrix being done with the phase encode gradient incremented every TR seconds. And that's why MR scans are the way they are. And basically, the take-home message of all this is MR scans take long and they're motion sensitive, therefore. Okay, why is an MR scan so motion sensitive? Look at this. If we were running through the generation of filling this data matrix, we were running from top row to bottom row. The whole data set is entered into the two-dimensional Fourier transform to generate the image. So if now somewhere during this experiment the subject moves, the data set that's acquired after the motion does not correspond to the original representation of the object in Fourier space, and therefore this creates artifacts. So here's an example of a subject that moved, and this produces ghosting and ringing artifacts, sometimes very horrible, sometimes rather subtle, but this is an issue that one has to deal with, and it's just a consequence of the way the data is generated. Okay, now, the maximum gradient that one applies, the maximum Kx or Ky, determines the resolution. That comes from the Nyquist theorem from Fourier transformation. So the stronger the maximum gradient is, or the maximum Kx or Ky, this is the biggest the biggest resolution that you can have, that defines the resolution. And the increment by which the gradient is incremented between data points defines the field of view. So there is nothing in the image formation with MRI that implies a spatial dependence of the reconstruction process or a spatial variation of the sensitivity. Fourier transform is in that sense not dependent on space. The resolution that you obtain is the same for every pixel. This is unlike the X-ray techniques that we've talked about, where the resolution of the image depends strongly on the detector geometries, for example. The limit that one has with magnetic resonance, one has to remember, the signal is proportional to the magnetization in the voxel. So in principle, one could generate an infinitely large data set. Will take an infinitely long time to acquire. That's besides the point. But in theory, you could. But the limitation is that one still needs sufficient number, a sufficiently high magnetization in a voxel to have a signal that's above the noise. So that's the limiting factor, aside from time. Time is not an issue. Okay, so there's one particular point that's of interest, and that's the center point of K-space here. That's this point here. That's where Kx is 0 and Ky is 0. That's the center of K-space in the image. That's actually where the contrast information is contained. So at the center of K-space, the information about contrast, about relaxation is in there. At the edges of K-space are the fine details of the object. So I'll illustrate this with some effects of incomplete sampling. So this is a 512 by 512 matrix. This is what you see on the screen. This is what you want to look at. This is a brain. This is what the computer collects. So this is xy. This is kx, ky. This is what's measured. After Fourier transformation, this is what you get. Yeah, you can think about what your brain looks like, Fourier transformed. That's actually what the scanner sees. Or your hand, or whichever object you want. Now, if you only collect the central 8 points, then this is what the image looks like. Very little information. If you take out the center 8 points, then you get the fine features, the edges. If you take 16 by 16 from this data set, it's the same data set, just collecting the central 16 data points, then you get this image, very blurry, but start to see features. This is 32 by 32. So this is the part that defines contrast. The outer points in K-space define the shape of the object, the resolution. That's actually an intrinsic property of the Fourier transformation. And to give you an example here why the center of K-space determines the contrast of the image, then the center of K-space is defined as the Fourier transform of the magnetization with Kx and Ky equals 0. And now we'll look at this with a discrete Fourier transformation. So we'll employ two things. That's the discrete Fourier transformation is periodic, and it's invariant to time shift. So we can time shift in a discrete Fourier transformation. So our echo that's recorded, this is equivalent mathematically to this. We just time shifted the entire signal by half the window that's been acquired. So this part here will now appear on this side of our discrete data set. So that comes from the discrete Fourier transformation. So that's equivalent. And what we have now is, from the Fourier transformation, is that the time point at time 0 is proportional just to the magnetization. So that contains the contrast. What happens later here is encoding of position. Just if you look at the one-dimensional transform we had for spectroscopy, I talked about that the time point 0 is proportional to the magnetization, which means in Fourier space it's equal to the integral. Okay, 64 by 64. Now the image starts to become interesting. Take out the first 64 points. This shows you that at the edges of the K-space are the sharp features, at the central are the broad features and the contrast. 128 by 228 and 256 by 256. That's what it looks like. Okay, well, I think we'll stop here. There is on the last slide, there's a summary of the spatial encoding with gradients that kind of summarizes what we've been talking about more on the mathematical side. And I'll try to retake the description of image generation next week.